Hello all. Today in this lecture we discuss about modeling of a control system. Control system has to be mathematically modeled as per the physical law governing its element. So now in this chapter with transform domain mathematical model have been developed. There are two modeling parameters, electrical networks and mechanical equivalent model. So control system is interconnected of a physical elements arranged in a plane manner. Now consider for electrical network. Now just for a consider for electrical network, say here on resistance. This is basically a low pass filter circuit or also known as integrated circuit. We present this network in a Laplacian domain. Here current is Is and the impedance is 1 by Cs, and this is a real part R2, and this is output Laplace transform of the output response VOS. Okay, so now this is known as phase lag network. Okay, this is known as phase lag network because the output voltage is phase lag with respect to the input voltage. Okay, that means output is that the input and the output are phase difference with the angle theta. The output is lagged by input, that's why it is known as phase lag network. Okay, so now what is the equation of the input equation? Solve it. The input equation equals to R1 into Is, applying KVL. R1 here voltage drop plus R2 into Is, this voltage drop, and Is divided by capacitor impedance 1 by Cs. So now if we rearrange this equation, we get V output equal to R2 into Cs plus 1 divided by Cs into Is. Okay, because V0 S equals to R2 into S plus Is by Cs. Okay, so here we see that V output equals to R2 into Is plus something. So from this equation we compute this mathematical form. It's very easy. Now therefore transfer function, we know that the transfer function is basically output Laplace transform of output response divided by Laplace transform input response, all initial condition equal to 0. If we put this value, then we get this R1 plus R2 to Cs plus 1. Okay, so now when again we write this equation by this expression 1 plus ST1, these two parameters T1 and T2 are very important because here T1 equals to R2 into C, this is a time constant parameter, and T2 equals to R1 plus R2 into C. Okay, now this is represented in a block diagram form. So what is a block diagram? The block diagram look like a 1 plus ST1 plus 1 plus ST2. So now this is a input Laplace transform input response, is a Laplace transform of the output response. Okay, so now this is known as a phase lag network. The corresponding phase lag network, the Laplace transform and the block diagram representation is shown by this figure. Okay, now consider the mechanical system. So what is a mechanical system? This is also known as translation mechanical system. This is very important. The equivalent model is here one spring is attached, one mass, and this is a known as damper coefficient F of the particular media, that is at this media. There is a spring, the spring constant equal to K, and here applied force equal to Ft, and displacement say equal to X. So this is a mass M, and this is a damping coefficient, or known as damper, for this particular media. Now the mass of the system equal to capital M here. So the mass of the system equal to capital M here, which is unit of M is kg, and the displacement of mass due to force applied, if we apply force in this mass, that is the amount of force equal to Ft in newtons, result in an inertia force. This inertia force is product of the mass and its acceleration, the spring deflection coefficient is capital K, which is capital K, which is Newton per meter. Okay, and the restoring force is Fk, is a restoring force Fk for the spring is proportional to its displacement. So this restoring force is always proportional to the distance x. Note down, student, please note down, this is very important. The viscous damping in the system is offered by a damper. The damping force varies in direct proportional to the velocity. The coefficient of viscous damping is F, which is also known as viscous damping coefficient is F. Now applied force Ft to the mass result in displacement x in meters. So therefore the equation of motion for a system obtained by the apply Newton's second law of translation motion, we already know that. That means we already know that what is the law? That is inertia force is equals to force acting on the mass. Okay, so now this is m d2x by dt2. This is basically acceleration dt2. Okay, I can write, sorry, this is a dt2, this is basically acceleration, minus of F, this is a damping force which is related to velocity, that means dx dt equal to velocity, minus kx, that is known as spring restoring force, and plus Ft here. So this is our equation of the mathematical approach representation of Newton's second law equation. So now if we rearrange this equation, this is a very easy task. So if we rearranging this equation, so therefore we getting the formula m d2x by dt2 plus f dx by dt plus k into x. Okay, so this is our main formula for this mechanical system. Now we convert this equation in a Laplacian form. We already know that. So this is in the left hand side, this is equal to fs, and what is the Laplace transform of second order differential equation? So this is equal to a square equal to m into xs, because all initial condition equal to 0, and next f into xx plus k into, yes, right, xx. Okay, so now if we consider or if we compute our some transfer function, then this equals to ms square plus fs plus k. So this is our first transfer function related to the mechanical system. Okay, for this system. Now we consider two analogy. One is force voltage analogy, also known as AV analogy. This is a force voltage analogy. Consider here our electrical network of voltage ET, EMF, resistance R, inductance L, and capacitance equal to C. Now current I is propagating in this circuit. So now according to the equation, KVL equation, we know that L di dt plus IR plus Q equal to CV. That's a dq dt equal to CV. So that's what here in the voltage from V equals to C, Q by C. So Q equals to basically integration I of dt by C. That's why you write here. Basically this is from the coming from the KVL, because this voltage equal to this plus this plus this. So that's why here 3 voltage are adding up. So now if we expressed this equation in a charge, so therefore L, we know that I equals to dq by dt. So therefore this equation is replaced by in this form Q by C and ET. Okay, so this is another equation. So now if we compare this equation with this equation, okay, that's why it is known as force, that is Newtonian force for this particular mass F, for a particular mass. And if we consider this equation, so now we see that now if we write here this equation again, Ft equals to, what is our equation? It's look like the same, Ft equal, that is here and here, equals to m d2x by dt2 plus f dx by dt plus kx. Now we compare these two equation, getting some parameter. First of all, number 1, We see that this applied force equals to this. Now applied force Ft is analogous to applied voltage Et. So these are first coming out point. Number 2, mass is equivalent to analogous to inductance. Number 3, resistance of the electrical network is analogous to, yes, right, what is F? Frictional coefficient. Number 4, spring constant K is equals to basically 1 by C, that means capacitance of the circuit. And last one, final, displacement is equals to charge of the electrical network. So that's why it is known as the analogous circuit. Okay, so this is with respect to force voltage method or force voltage analogy. Now we discuss another thing which is followed by coming out from the concept of KCL. It's known as, yes, right, force current analogy, or also known as FI analogy. Okay, it's just vary the name. So now for this, for the circuit consider, say for the circuit consider here one current source, say for IT, it's one current source, and here you consider one inductance L, here you consider one resistance, and here one capacitance. Okay, so now here the current equal to IL, here the current equal to IR, and here the current equal to IC, and the output voltage equals to EMF. Okay, so now if we follow our KCL law, then IT equals to IL plus IC plus IR. So this is very easy equation. Now what is value of IL? IL equals to 1 by L integration dt. Okay, edt, sorry. Okay, but because V equals to LDI dt, so therefore I equals to basically integration of 1 by L V by L dt. So in this problem, V equals to, we consider E here. So what is the value of IR? IR equals to basically EMF by resistance. What is the value of IC? C dV dt. That means this, because Q equal to CV, and now if we take the derivative, that is equal to current, that is equal to C dV dt. So here voltage is equal to E, small e. Okay, so now putting this three equation, 1 by L, that is integration E dt, plus 1 by R into E plus C into dE by dt. One thing should be known, this is a C and this is EMF E. Okay, otherwise it will not notify the wrong parameter integration. This is a C, this is a E. Okay, so now this is our KCL equation. Okay, and just for a consideration, so this is our KCL equation basically. Okay, so now if we express this equation in a form of charge, okay, so this equation equals to E one thing should be remembered, that the voltage here E is related to the flux linkage associated with the inductance L. Therefore we consider E equals to d phi by dt, flux linkage. Okay, so now if we put here this value, therefore we see that D is equal to left hand side phi by L plus 1 by R d phi by dt plus C into d2 phi by dt2. Okay, the right hand side is IT. So if we rearrange this equation, then first the second order derivative is coming out, C d2 phi by dt2, plus then first order derivative 1 by R d phi by dt, and then the term phi by L, this is equal to IT. Okay, now we are coming from this equation. sorry, this is now we consider for this equation. Okay, now comparison with this equation. Okay, so now write here again, that is m d2x by dt2 plus f dx by dt plus kx equal to ft. So now what is analogous? Current is analog to force. Here k equals to L, displacement equal to phi, dx by dt, this is equal to this. That means here small f, that is our small f here, the viscous friction coefficient, it's equivalent to, yeah, right, 1 by r, and mass equal to the capacitance. So just it opposite for the current, force current topology or force current analogy. Okay, so this is the equivalent model, equivalent mechanical system comparison with the electrical system. That is our first topic in this class. Okay, so now we discuss about rotational mechanical system. That is much more important. Okay, the moment of inertia of a system considered. Now our next topic is rotational mechanical system. Okay, now consider moment of inertia of a system. So consider J. Okay, the inertia torque developed in the system equals to J into alpha, where alpha is the angular acceleration produced due to the applied torque capital T, and viscous damping is offered by the damper, and the damping torque varies in direct proportional to the angular velocity of the shaft, and the coefficient of viscous damping equal to F, small f. Say consider for this picture. Now consider this for picture. For the rotational system, we consider this diagram. Here rotation, here this is the angular speed, which is known as omega equal to d theta by dt, and this is applied torque, this is a T, and this is a J, and here for this system one damper is used known as coefficient F by F. Okay, so now according to the Newton's second law for the rotational system, we know that inertia torque equals to torque acting on the system. Therefore, what is the value of inertia torque? J alpha torque, and minus F of omega plus capital T. So this is our torque acting on a force, and if theta is the angular shaft shift in radian, then you already know that omega equal to d theta by dt, angular velocity, and what is alpha? Alpha equal to d2 theta by dt2. Okay, so now substituting this value in this equation. Okay, so now J d2 theta by dt2 is equals to minus f d theta by dt. So again we see that this is another form of, is a second order differential equation for the rotational system. Okay, now we see that is equivalent to d theta by dt2 plus f d theta by dt equals to t. So again we see that, so now we are assuming all initial condition equal to 0. So now we take the convert in a Laplacian domain, that is equals to theta s f s, this is theta s, and this is equal to ts. So now what is a mathematical form of theta s by ts? That is equals to 1 by js square plus fs. So this is the modeling. So this is the transfer function relating to the rotational system of angle theta, and that produce a torque and the interrelationship between them. Okay, so this is very important for the rotational mechanical system. Okay, so now if we consider from this equation, if we consider the equivalent diagram, so Ts, our torque, is basically, for the analogy, is equivalent to current source. I just comparing the analogy here. This is a J. Okay, this is a J. and here the damper is F, because this F is basically d theta by dt, and this is equals to J, inertia of the system. So these are equivalent. In the later video we'll discuss about the thoroughly concept or the mathematical problem related to this mechanical system, because it compares the electrical system and vice versa also. Okay, so that's all for today. In this class we just talk about the basic modeling criteria and basic modeling. What are the basic modeling parameters? Okay, thank you.